this is, I'm just going to treat this kind of like a lecture. I'm just going to go through these examples, right? And then if anything comes up, just ask it, right? Because the key to doing well on this exam is making sure you know what every single step is doing. Like, why is an arrow pointed a certain way? Why is it pointed another way? Right? Why is it positive? Why is it negative? If you don't see that, you're not the only one that doesn't see that, right? So bring it up. Make this as interactive as possible. Okay. So again, I mentioned this a lot of times. There's two problems, or they're just like homework problems, right? Where I'm going to get them is I've got like 8 dynamics books on my desk, or on my bookshelf behind where I sit. I'm going to reach over there. I'm going to grab them. I'm going to flip through them. I'm going to go to the similar sections. This stuff hasn't changed in 100 years, right? Like, this is the same material. So those old homework problems work just fine. And then I look at it, I go, can I do this? And I was like, yep, I could do this. And then I will grab it and I'll just copy it and put it onto this exam, okay? And so there is no conceptual questions. It's just, can you work out the problems, okay? The 2 types of problems they're gonna be is one kinematics problem, so the geometry of motion, right? And we'll go briefly over that in a second. And then one force equals mass times acceleration. You get 1 page of notes, single-sided, handwritten, your handwriting, fresh handwriting, okay to make it on a tablet and then print it. And I have to put all those words in there because, again, what I've run into in the past is people just take like the notes from their tablet and squish it down and put it in, because you could do that really easy. You can copy it and scale it and put all of the notes in there. So Chick-fil-A, that's nice. Good work. Yeah, you just seen this place when that opened up this summer, when it opened up the first time. There's massive lines going outside the door. All the community came here. They're parking where they weren't. They're handing out parking tickets all over the place because people. Anyways, it's a big deal. It's a big deal at Bozeman to get a Chick-fil-A. And so I want the point of the cheat sheet. Yeah, it's nice to have that crutch there, right? Just in case you forgot an equation or something like that. But really, the main reason is it's a tool to make you study, because you have to sit there and go through your notes and pull out what you think is important. It's a little trick that I have to get you. And actually, most faculty is, because usually if you've studied right, you don't need to look at that. But just in case, it's nice to like go over there and look. I would stay away. I'm not going to absolutely outlaw it, but I would stay away from putting examples. I run into problems where students run into problems sometimes because then they try to do it like, oh, does it match this problem, or does it match this problem, does it match this problem? Like, it doesn't work as well. It's just like writing down the equations and studying the examples yourself and knowing, because I'm not going to give something that you've done before. So, all right, any questions about that, right? And so there were some questions of like, when I say fresh handwriting and your handwriting, I just mean don't copy it and put it in from the notes, and then don't grab someone else's, because that's the other thing I've had is students have made a cheat sheet and then they've handed it out to everybody, and so everybody has like a really nicely put together. I want you to do it, okay? But it's okay to make it on the tablet and then print it out, okay? It's just funny to say no calculators because I've been preaching it, but really, absolutely, please bring calculators. Yeah.
I've been requesting to remind you to record the session.
Got it. Got it recorded. Yep. No, thank you for that. No calculators, just joking, but please bring them, use them as much as possible, learn how to use them, okay? Absolutely. Keep it tight, follow the plan. All right, I've laid out how I want you to solve these problems. Try to stick to that plan. Keep it really clean and easy to grade, right? Because also keep in mind, right, I'm going to grade, there's 101 of you. I'm grading 101 of these things. If you have it nice and laid out and beautiful work, it's just, I'm going to be in a good mood and I'm going to give you a good grade. I'm going to give you most of the stuff. If it is shit written in the margins, stuff written on the back, sitting all over the place, bad handwriting, written sideways, I hate that. I absolutely hate that. I'm going to be mad at you and I'm going to give you a bad grade, okay? I know sometimes, though, it's panic, right? Panic mode steps in, and then you're like, oh, my God, I tried this. I tried to be clean, but then panic happened, and then you know, I get it. And if it happens, it happens. But still try to keep it tight. Keep it tight and follow the plan, okay? Kinematics, all right? So just briefly what we did. It's the geometry of motion. I will not require you to do an integral, okay? So like acceleration's a function of velocity, and then applying the chain rule to get into the right thing, and then switch to the thing, and then do integrate. We're not doing that, okay? I'm going to keep it pretty straightforward. This is going to be a little bit of a softball for you. Just if you saw the problem that I had you do, was just a projectile motion type problem, right? Just something along those lines I mean, it's a gift to myself too, right? So if it's easy, then it's easy to grade as well, okay? We're gonna start out with that. All right. All right. So then when we did kinematics geometry, note that 1D motion, 4 types of acceleration, those just kind of review what we did there. Then we did curved motion, we did Cartesian, normal, tangent, and polar coordinates. And then we also briefly talked about relative motion. Relative motion can be really important later on when we do 2D rigid body stuff. Which isn't too far off, by the way. We don't have too many subjects left. We have impulse, momentum, like impacts that we have next. That's the next thing we're going to talk about. And then right after that, we're jumping into 2D rigid body stuff where things get really interesting. Okay, and then in force, mass, acceleration, right? Accelerations, forces, times. There'll be some stuff, there'll be discussion about that. Okay, and we did this in Cartesian coordinates, normal, tangent, polar coordinates, right? And so we applied those, they all have the same methodology. They all involve drawing a free body diagram, writing down our equations of motion, doing kinematics as required, and solving. If you just stick to that plan, literally it will lead you to the right answer every time. It really will, right? And if it doesn't lead you to the right answer, it'll get you pretty damn close, okay? All right. So this is just for example, this is last year's breakdown of grades, right? This is not a bell curve, right? There's a big chunk just to scare you a little bit. Yeah, big chunk of people over here, right? In the 45 so this is out of 50, right? Out of 50. So this is, in the 90 to 100 range, a big chunk over there. And then there's a little bit of a bell curve here. But the average was just 62 or 63, right? So it's not easy, right? It's not easy. And so I did this, I analyzed this from last year, or actually this is 2 years ago, I think, the breakdown. And I analyzed it, it's like, why do I think this is happening? So here's my theory of why, and this is what you can avoid, right? Poor cheat sheets. I think some people are just like, just real quickly and just, right? I'll show you an example, I'll do that right now. I'll show you an example of, this is a cheat sheet from one of the better students, right? I wrote a lot of shit down there, right? They wrote a lot. This is a little bit different because it used to be that we used to do the 4 questions all the way through particles. They used to do all 4. So this is probably double what you would have to do because this is it. I mean, he's even worshiping the devil in there as part of it, right? He's getting a little crazy with it because he's like, oh my God, But anyways, just you write it all down. Spend some time with it. Put together a nice cheat sheet that you can trust. Okay, I think that was part of it. Just not spending enough time with that and putting something together, right? Not sticking to the plans, stick to the plans. Not taking serious, that's a big one, right? We're just like, this is gonna be fine, I did calculate it's 12.5% of your grade, right? So that's a big deal. Each one of these things, I call them quizzes, but really they're exams, right? They're half an exam. I guess they're half an exam, right? So please take it serious. Just, you don't hardly have any homework in here. I'm sure you have nothing in any of your other classes, right? It's always really, it's easy for me to say. It's like, let's just spend a bunch of time on this. But you have probably 4 or 5 other classes you got to deal with. I get it. I was there once. I'll tell you this, it's way better being on this side. Right? I mean, I really enjoy exams. I just come in, we just sit down, just watch you guys squirm. It's actually quite pleasant. I love test days, right? I used to not. When I was you guys, I definitely did it. Okay? Copying your homework, right? If you're just copying your homework and not spending time learning how to do it yourself, that's a little too late at this point, right? If you were copying your homework. Not using your calculator to the fullest potential. There's a lot of wasted time that goes into algebra when they're solving these things and then documenting all your steps. So using it to your best, all right? My advice to you, study, right? Better cheat sheets. Learn calculator, it's your friend, all related to the stuff up above. And then if you're looking for ways to study, right, go through everything and then work out example problems from old exams, right, which we're going to talk about right here. Also, to add to that, go through your homework. Make sure you know how to do all your homework problems. If you know how to do all your homework problems, you're going to be just fine, okay? Also, if you want a little extra practice, go to one of those homework problems and grab one of the ones right next to it because they're all going to be similar, right? Grab one of them that's right next to it and see if you can do that, okay? Stick to the plan. Some people don't even have plans. That's a true statement, okay? Easy exam, ride to the occasion, neatness will make a difference. It really will. Tight pages, right? No reason behind every step. That's a big one, right? Make sure that's one thing that's nice about mechanics is there's a reason for everything and there's an exact answer to everything. It's beautiful, right? So make sure you know all of those little steps. And if you do that, you're going to be just fine. Use resources available to you. That's like use the learning center if you can, when it's possible. I think Aiden has some hours in there tomorrow, so if you have any other questions, you can go in there. Swing by and see me, okay? No, it may suck, but I may have to fill a bunch of you. That's the other option, is I just fail you, right? And I do it, like I said, about 15% or 15 to 25% don't make it through this class, right? So that's a quarter of you. It's just 25%, that's a quarter, by the way. That's a lot, right? That's a lot. Do I fail 25% of the people that try? Hell no, right? I fail 25% of the people overall, and most of those people are not trying, right? They're trying to skim by and not putting their full effort forward. What up? No, you're welcome. Come on in. We're teaching dynamics really quick. If you, all right. I just always like to share these. This is pretty fun. I've actually been in this situation before, right? When you're in the middle of an exam and teachers explaining something to someone else, you just make sure you get those. Listen. You pretend you're not listening, but then really you're listening to what they're talking about. That's a big one. This is also a pretty good one too. When he walks up to you to the exam, looks at your paper, and then shouts, "Guys, please make sure you read the problem. Like, clearly you did something wrong." And so they're like, "Hey, you should adjust that." I thought it was pretty good. Okay. All right. Let's do these, okay? Particle kinematics, right? Again, this isn't open notes, right? You're going to do a cheat sheet in this thing, okay? So this is, remember I said, this is during COVID years. This was Tom and Calvin, everything involved Tom and Calvin, right? I don't know why. I'm trying to relate to you guys, right? I'm trying to relate to everybody in here, and throwing beers off of rooftops. I think that's a cool thing to do, right? So anyways, so that's what's happening, right? Tom is throwing a beer to Calvin. So here's Tom up here. He's throwing it up like this, and it's coming down to Calvin down below. I made this all by myself. This is during COVID. I had a little extra time. I was like, let's make this interesting, okay? So he's throwing that thing. And so what we're asked to find is the minimum initial velocity, V naught, required to clear the edge of the roof of the smaller building at point B. So he's going to throw it, and what's the minimum velocity to clear this point right here? Okay. What do you think a solution strategy would be? Yeah, curve motion, right? What kind of motion is it? Projectile motion, right? So this would be a good thing to put on your note sheet, right? Like you could go back from the very beginning and you could derive the potential or the projectile motion equations, right? But if you have that written on there, grab those sons of bitches, right? And so then I have those projectile motion equations, and I have them for position, right? So I have those things for position. And so what about the position? What do I know about the position for this problem? Yeah, that's right. So it has to go 10 feet in the X, and then what in the Y? Yeah, exactly. I basically aim for this point. So what I do is I just write the X equation as a function of my X position is a function of time. I have an equation for that. A Y position is a function of time, and I set those equal to that coordinate system right there, or to that coordinate right there. So that right there, that would be then, and then I should be able to get the minimum velocity. So let's do that. Okay, so like I said, right, I'm going to jump right to that. Again, if you could derive them if you want. I'm not going to dock you for deriving them, right? But just, it'd be nice to have those in there. Oh my gosh, I got all sorts of stuff going on here. 202. Okay, so let's do it. Right, so problem one, right? And when I answer this, I'm going to try to be as clear as possible. Like, this is the first question that I've asked to solve, right? And in this equation, I can get x as a function of time is equal to v naught times cosine of 30 times t. Right? So if you looked at the projectile motion equations, that is something that's in there, right? X is a function of time is v naught times cosine of 30 times time, right? So it is the velocity component in the x direction times time will give you position. That's a pretty straightforward. There's no acceleration in that direction, right? And then y as a function of time is equal to v naught sine of 30 times time minus 1/2 gt squared. Right, so that is my y position as a function of time, because it has an acceleration component in that direction. Okay, so those are equations. Okay, so at this point, literally I go like this. I set this equal to 10, and I set this equal to negative 11. Right? Where did I get those, right? I got those from this guy right here, right? He's, right, the Y position, right? It's gonna go down 1 and then down 10. So that would give me the Y position of this location right here, right? And then to the right, it's gonna go 5 and 5, and so that's gonna be 10 right there, right? So at this point right here, I solved those two equations, right? Two equations and two unknowns. What are the unknowns? V naught and time, right? Those are the two unknowns in this equation. That's it. That's only the two. There's only two unknowns there, right? I know G, I know V naught, or sorry, I know G, I know sine of 30. I said the only unknowns in there are V and T, okay? And so you could do that via substitution. You could do it the smart way. You could put it in your calculator, solve that system of equations, and we get V naught is equal to 6.24 meters per second, and T is equal to 1.85 seconds. Man, very easy, very easy. And we did a very similar problem to this. Remember, we had the cannon that was shooting down and the thing was moving to the side. We had that where we set the position that we did this exact same thing. We set the two positions equal to each other. Actually, that problem was even more complicated because Calvin would have been moving around down there, right? Which you could do, right? If I said Calvin is moving around, I would do the same thing that I just did right here. I would say Calvin's moving around. I would come up with an X position as a function of time for Calvin and a Y position for Calvin, which would just be 0 or would be 1 in this case. And then I would do the same thing. I would set them equal to each other. The X position and the Y position of both objects that you would set equal to each other. All right? Everybody see that? Go. All right? Problem 2. Distance D that Calvin should stand in order to catch the beer, assuming it was thrown at the minimum velocity of part A. So if we threw it at that 6.24, where would he need to stand, right? That's a very unknown right here, that D. Where would he need to stand in order to catch it, okay? Thoughts? Thoughts on that? Yeah, so same idea, right? I'm just gonna go at X as a position of time, and Y is a position of time, and then I'm gonna set those equal to the coordinates that I need there. And the D is gonna be an unknown in there. So let's do that. X is a function of time. Now I know V naught, right? The V naught we just solved for that. Said if we throw it at that same V naught. So this would be 6.24 times cosine 30t is equal to, right? So what is that position? What would that position in the X direction be equal to? 10 plus D. 10 plus D. Right? Because I know that this distance right here, that's 5, that's 10 plus the distance D. Right? So this would be 10 plus D. Right? And then Y is a function of time. That is going to be that 6.24 sine 30 times t minus 1/2 gt squared. What's that going to be equal to? Yep, minus 15. Right? Because that way it'll be, 1, 10, that's 11, down 5, that's 16, back up 1, that'd be 15. So negative 15 in that case. Right? So now, same deal. Two equations, two unknowns. Boy, you need to learn how to use these two equations, two unknowns thing. You gotta get this, right? This is twice now that we've done that. Sure, you can do it in substitution. Oh, that's a pain. That's a pain to do that, right? Because you got the sine 30t. You could do it. You could solve for t. Oh, that's not too bad. You solve for t, and they take that t, and they put it back down and solve for v. That's as easy as doing it with my calculator, right? So two equations, two unknowns. Again, the two unknowns is going to be time again. Time is equal to, what did I get? 2.09 seconds. All right, and then this case, the D is the unknown, which is 1.32 meters. Okay? Go. 3. the magnitude of the velocity of the beer when it reaches Kelvin. Okay, 3. Any thoughts on that? Yeah, so I have to, yeah, that's exactly right. I gotta calculate the velocity. I mean, that's what I do. I gotta get the velocity of it down at the bottom. And then I do the square root of the sum of the squares of the 2 different directions, okay? And so I gotta do that right now. This would be, the velocity. This again would be in my equation sheet. I have the velocity. That's just gonna be 6.24 times cosine 30. Okay, that's just the velocity in the x direction. And it's not a function of time. It's constant, right? It's constant because there's no acceleration in the x direction, right? There's no drag. We're ignoring drag. And so this would be 5.4 meters per second. And the velocity in the y would be 6.24 times sine of 30 minus gt. And so I need a t there. That t is going to be this one. All right, I'm going to plug that t into that down there. And so this ends up being equal to negative 17.4 meters per second. Right, and so then the magnitude would be the square root of the sum of the squares of both of those. Let's say this. The magnitude is equal to 5.4 squared plus negative 17.4 squared. And there we get 18.2 meters per second. And then the last one was just the last part of it. I don't know if you had that. I don't know if that's on your write-up or not. Is this a good idea? And I think I just want to it's always important when you solve these problems, just be like, just a little gut check. Like, is this possible? Is this a good idea? Is this a bad idea? One thing, catching something that's going 18.2 meters per second. Fuck if I know. I don't know. I don't know. Do you guys know what that is? Is that fast? Is that not fast? Right? Oh yeah, you're a metric guy. It's 18.2. You can catch that, right?
Pretty fast.
Yeah, but I think it could. I did it out miles per hour. ChatGPT told me miles per hour of that thing was about 44 miles an hour. I could catch a beer at 44, right? I mean, people are catching, fastballs at 100 miles an hour. I could catch a beer at 44, right? I think I could. Yeah. Yeah.
The question would be, how long can you stop the velocity so that your impulse doesn't blow up the can?
That's right. We're gonna do that later. That's the next thing. Impacts. Right. You want to increase that time of slowing it down so the forces are less. That's right. If you got some give there, you'll be all right. So I think it's worth a try. It's worth a try. I think I'd try to do that, right? I'd try to catch it. I mean, what's the worst that can happen? If it hits you, it might be a bad idea. Okay. All right. Let's do the next one. Tom and Calvin are pretty crazy here, all right? So Tom and Calvin got a hold of a crane during COVID days. So they got one of these things. They got this little man basket. Got a little man basket up there, right? And then I think it's Calvin that's in there. So one of them's in there. Yeah, Calvin is in a cage hanging from a cable, right? So he's in there, and then this thing is kind of in 3D here. It's an isometric view. It's rotating around with an omega there, and we're trying to find if the angle is 45 degrees. So we're going to hold this angle right here, that theta right here at 45 degrees, right? And determine the constant angular velocity of the omega. So it'd be one of those cases, that thing's spinning around in a circle, right? Or just the crane part swinging around in a circle. If you can imagine if he goes fast enough, Calvin will be straight up, right? And if he's not moving at all, Calvin will be straight down. So we're trying to find the omega that's holding there. They're very similar to several problems we did in examples. Okay, and let's do it. And you can tell us all the basic information we need there. Constant omega. The angle is 45 degrees. Find the constant angular omega required for that angle to be 45 degrees. Okay, so at this point, here's what you do: you start panicking. You stare at your neighbors. You try to peek at your neighbors really quick. Don't do that. But then you just like, what should I do? Oh my God. stick to the plan, right? We have a plan for solving these things, right? We're gonna do a free body diagram, we're gonna write our equations of motion, and then we're gonna do kinematics as required, and we're gonna solve. Okay, so then let's do it. Let's do it. Let me get my free body diagram here. Right, and you could do your kinematics first if you want. In our examples, we did them first. Let's do it. Let's do it for so it's important to, like, just to make sure we got our bearings straight, our coordinates straight. I'm gonna do this because we kind of need to know the coordinates for solving this. So, right, Calvin's gonna be traveling around in a circle. Okay, if you were to look down on this, Calvin's traveling around in a circle. Okay, and so some key things about this circle. Right, so he's over here at this point. Some key things is the radius, right? We should know what that is. Right? This radius R is equal to, right? I think a lot of you would want to do, right, 10, right? That's 10 out there. But is that the radius that Calvin's at? No, because there's still this component, right? There's that component that's sticking out there. So this little triangle here. Right? And so the hypotenuse there is 10, right? And so then I can calculate that. That should be 7.07. This is in metric, 707 meters. Right? And so my radius should be 10 plus 7.07. I'm going to do that in my head, 17.07. Nailed it. Hey. Except for it looks like a 12. Okay. So that's what that radius is. The other thing I'm going to do over here is I'm going to label the coordinates. So I'm going to say that guy right there. I'm going to do mine in polar coordinates, but you could do, this would be E theta. And then if I'm doing polar coordinates, then this is ER. Okay. And I've said this a bunch of times. You could also do it in normal tangent. This would be EN, and then this would be ET. Okay. You could do it either one. All right, it's up to you. Yeah.
Would one be easier?
Nope, they're exactly the same. Except for one has a negative and one has a positive on the centripetal acceleration. Other than that, they're exactly the same, right? Because it's traveling in a circle. If it wasn't traveling, if for some reason, that radius was changing, like if there was an alpha there, then that radius would be changing, the omega would be changing. There would be an alpha, and then this radius here, this R here, he'd be moving out, and so it would be like kind of like going in a spiral, and then you would absolutely have to do polar coordinates if that was happening. That would be a really good problem, but I think that's too hard to do this in that. Basically, you have 25 minutes to do it. It's too hard for that. Yeah.
Are we in normal tangent?
It's up to you.
Both.
No, one or the other. So I'm just showing you they're the same.
Oh.
Yeah, that's all I'm saying. Don't do both. Don't do both. It's either normal tangent or polar coordinates. When something's traveling in a circle, you could do either method, right? The only difference between them would be when we talk the centripetal acceleration, then you would have this one has a positive centripetal acceleration because it's in the positive EN direction. This has a negative because it's in the negative EN direction, or negative R direction. Centripetal acceleration would be going this way, and your ER is going that way. So you end up with a negative on the centripetal acceleration. Other than that, if it's in a circle, it's the same thing.
Do you think our polar is going to be easier because of the thing that, as far as a circle, and so our angular, I don't know what we're looking for, it's going to be in that direction anyways?
Either one works. They're literally exactly the same.
Really?
Yeah.
Yes. Yep, I'll show you. I mean, actually, I'm not going to show you because it's going to add confusion. But trust me, the equations become exactly the same, except this gets a positive centripetal acceleration, right? Because it's acting in the EN direction. This one, the centripetal acceleration is negative because it's in the ER direction. Other than that, it's exactly the same. The only way polar coordinates would be easier would be, again, if there was an alpha, then this guy would be, its radius would be increasing. So if its radius was increasing, we'd have Coriolis acceleration. We would have tangential acceleration. We'd have all this other stuff we're not including, right? And so we're not going to do that's too complicated for this. But that's that. So just be really careful. Don't just do. We're going to do just E theta and ER. Okay. All right. So now let's come down. Now I'm ready for my free body diagram. FBD. Okay. Free body diagram. You got to isolate my object. Isolate my object. Okay. I'm gonna start drawing down my known forces acting on here. Okay. I have what we got acting on this guy. Okay. Gravity. Okay. Mass times gravity. What else? Tension in that cable. Anything else? So there could be, depending on like what you're looking at, right? So we're gonna, when we're talking this object, it throws people off. I'm gonna do the whole thing at once, right? The whole thing, right? Because then I don't, later on there's another question saying like, what does Calvin feel inside of here? Like what's its normal, because there's a normal force there, right? Calvin would be pushing on the bottom of this cage and there would be a normal force, but that would be if I drew a free body diagram of Calvin, but that's later on. But what really matters to me is the sum of the two together. They're stuck together. That's just one object. It's like, you know, it's just there. We're going to count them as one. So there's really just a tension force right there, right? Everybody see that, right? And then later on, we could slice it up and look at what's happening to Calvin, which is one of the later questions. But for now, though, it's just that's one total mass, the two of them added together. So there's just one tension force, mass times gravity. That's it, okay? But we're not done with our free body diagram. We also have to label the coordinates. And I think this is a really key step to it, right? This is going to be ER. Okay? And this is going to be K. ER and K. Now, where is E theta? Into the page. Into the page. Right? Is there anything happening in that direction? No. Could there be? Yeah. Yeah, there could. If there was an alpha, back to the problem. If there was an alpha, there would be a component of T. T wouldn't just be straight up and down like this. T wouldn't be straight up and down like this, right? It would actually have a component going into the board because there'd be some acceleration there. So T would actually have a component into the board. We don't know what that is, right? Trust me, I don't think you guys are smart enough to handle that. But you could, honestly, you could. If I gave you enough time, you could just relax a little bit and work your way through. Our methodology could handle that. Absolutely. There's enough knowns here that you could absolutely do it. I have faith you could do it. Although, I won't make you do it. Or will I? No, just joking. I won't. Okay, and then I'm still not done. Let's add some dimensions here just to kind of, oh, and I like to do this too. I like to just show the break here. The two different components of T. If I can do this. I could do it. Right? So T, I should put it here. T is going to have two different components, and I know this angle right here. That's going to be 45. They're both 45. 45, 90. Okay? That's it. There's our free body diagram. Again, really important to do these on these problems, right? To nail them, right? Because if you nail this, it's so clear. It's very clear what we got to do, right? When I go to look at what forces are acting on stuff, it's right there. When we write the equations of motion, it's literally everything's written right there. Do this. Okay. So now equations of motion. Next step, right? 2 E O M S. Equations of motion. Right. Start writing them all down. Some of the forces in the theta direction is equal to mass times acceleration in the theta direction. Okay. First, there's no forces in the theta direction, and there's therefore no acceleration in that direction. You could go like this. This is mass times, what is it? The theta direction. Is R alpha plus 2R dot omega. Tactically, I should, yeah, you could say T component, T theta would be equal to M R alpha. That's probably what I should do. If I want to be complete here, I'll probably call this T theta. Because technically we don't know that T theta is equal to 0 at this point. But, so then I just go, okay, well, what's alpha? Right, where did I get this, right? I got that off my spreadsheet. Or actually, I got it in my head here. But you get it off of your cheat sheet, right? Because that's the acceleration in the theta direction. Acceleration in the theta direction is R alpha plus 2R dot omega, right? The Coriolis, right? The Coriolis and R times alpha. So in this particular case, right, alpha is 0 because omega is constant, right? So alpha is 0. And then R dot is 0 because it's not, that radius is not expanding at all. It's a constant radius, and so that R dot is equal to 0. So then this whole thing is equal to 0. Right? There's 0 acceleration, which means there's no t in the theta direction. Okay? So that's it, right? I mean, I write out what all my forces are in that direction, and then I set it equal to mass times acceleration in that direction. In that coordinate system, the acceleration in that direction is R alpha plus 2R dot omega. Both of those are 0. All of it's 0. Okay? Now, sum of the forces in the R direction is equal to negative T, right? So again, what I do is I come up here and I look to see what's in the R direction. Well, I've got this. That's it, right? It's acting, that's the only component, the component of T in this direction. Okay, that's the only force acting that way, right? Is that positive or negative? Negative, right? It's negative because ER is pointed that way, EN is pointed this way, right? So this would be, or E theta. So this would be T cosine 45 is equal to M A R, which is equal to M times R double dot minus R omega squared. Okay, R double dot is 0, right? Because that radius is not changing. It's not accelerating in that direction. Okay, so that's it. So at this point right here, if you were doing this in normal tangent coordinates, this would be a positive T cosine theta, and this would be a positive R omega squared, because they both would be acting in the positive EN direction. And so either they're both negative like we have it, or they're both positive if you do in the EN. That's the only difference that you would get. Okay. So then, okay, that's equal to negative R. This is equal to, so the resultant is just negative M R omega squared. Right? And we don't have enough here, right? I'm after this omega, right? I'm after that omega, but I also don't know what T is. So I got one equation and two unknowns at this point, right? One equation, two unknowns. So I got to keep going. Sum of the forces in the Z direction is equal to T times sine of 45 minus mg, right? So where did those come from? They came from my free body diagram. There's this guy. That's the T sine of 45. And then I got a mass times gravity, right? This one's positive because it's acting up in the K direction. This one's negative because it's acting in the opposite direction of K, the negative K direction. So that's what that guy is. And then that's equal to mass times acceleration in the Z direction. What is acceleration in the Z direction? 0. Because we're trying to hold this thing steady, right? It's going around and we're going to hold it at 45. If we're holding it at 45, it is not accelerating up, it is not accelerating down. So that is equal to 0. Okay. So then there it is. There's our two equations and two unknowns. This one's pretty straightforward though, because the lower one you could just solve for T. The only unknown in the lower one is T. And so you could solve for T and then take that T and put it back up and solve for omega. Or what I had to is put them both in my calculator. Boop, 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 boop. TI-84 guy, you got to learn how to do that. It's another two equations and two unknowns. Okay, remember, start dealing those drugs. Get that money. Get that money to get yourself Get yourself a TI-89 for Christmas, or Christmas is coming up. It might be too late for you, or it might be too late for you in this class, or it'll be just in time for next semester. Oh, yeah, that's a good time. Okay, so you plug that in there, and you get my tension force is equal to 2774.7 newtons, right? And then again, I'm really bad with units. I just am super smart, and I just make sure I put everything in terms of newtons and meters and second. And you know, if you can't do it, then be careful, right? Then do what you need to do and put your units all around it, right? That's fine. I mean, that's what I should be doing, except for I'm a tenured professor. I don't care. I don't like units, and I just keep track of it in my head. And you guys, I've made it this far in my career with just being blatant and disregard for units. Because nothing I do actually will get implemented. I think I would need to, like, if I was a real engineer, I think I'd be a little bit more careful. Like, if I was launching rockets into space, like, I think I'd be a little more careful with my units, right? Okay. That is, I will say, whenever I get the wrong answer on something, that's the first place that I look, is where is it my units, right? Is it off by a factor of 12? That's a big one. That's a big one in structural engineering, because you do use English units in structural engineering, and you're always going between feet and inches. And so if you're off by a factor of 12, you're like, oh, that's a quick solution. Okay. All right. Second problem, or second part of the problem, right? This was all one. Right? Most of your points was with this. Right? Part one said, if the angle is theta, determine that, right? And I didn't do the breakdown of the points, but I think that was worth the majority of it. Okay. The second was, how many g's of acceleration will Calvin feel at this angular velocity? Okay. How do you think I would get that? Like, what is my acceleration that they would feel? Huh? R omega squared, right? It's the AR component, right? There's two components. There's AR and AZ, but what's AZ? Zero, right? Yeah, and then technically there could also be an E theta. An acceleration in the theta direction, but in this case there is not, because we already determined that there's no acceleration in that direction. So really all Calvin's going to feel is AR. So then what you come down here, part two. Okay, part two. AR is equal to negative R omega squared. Right, and actually, if you do that, you plug in that omega we just got, and the radius that we had up above. This ends up being 9.81 meters per second squared, which so it's gravity is what you would feel, right? And that's tied to the fact. Right, tied to the fact that this is 45 degrees, right? But he would be feeling an acceleration back towards the middle of 9.81, right? And so the centripetal acceleration would be gravity. He'd be feeling gravity as it goes around. Right? Cool. Yeah.
So in your solution, you had it as negative 1g. And I don't know if the negative is like intentional or where that came from.
Oh yeah, it is. It is.
So
I just left this negative. It is right here. I didn't put it in there. This negative 9.81 meters per second in the ER direction.
So if you were working in normal tangent, would it be?
It'd be a positive 9.81 in the normal direction.
Relative to your coordinate system?
Yep. That's exactly right. Right, and because again that centripetal acceleration, right, is this person Calvin must be accelerating back to the middle. If he's not, then he's flying off on a tangent, right? And so he's accelerating back this with 9.81, and our ER direction is that way. So that's why it's negative, because he has to accelerate back that way. Okay? Cool. Yeah.
So if we're having G's in like.
Oh, did I not do a G? Oh yeah, I did divide by 30. Yep. So that's my total acceleration. So if you wanted this in G's, then you would do negative 9.81 divided by G, which would be negative 1 in the ER direction, right? Because that's what 9.81 is G, right? So that's a great question. I guess that I answered that. I wouldn't have docked you for that, by the way. If you didn't give it to me in G's, I wouldn't have docked that. It's good. I'd be so proud of you that you got that far. Right? I'd be like, sick. He did it. I love it. I absolutely love it when I'm grading these, right? Because I do them on grade scope. And so I have a little rubric set up, and it's a pretty coarse rubric. It's like, did you get it? Did you not get it? Did you kind of get it? Did you kind of maybe get it? Did you kind of more get it than not get it? Right? It's just like that. It's just like, and I start flying through it, right? Now I have little comments as I go through, but I love it when it's the right answer. Just right answer, boom, and I hit next one, next one, next one, next one, next one. It's phenomenal. Then okay, all right. Okay, so a couple ones. The last one, part 3 here. Some of the and I usually do this. I kind of start out with what you're used to seeing, and then I just take it a step further and just say, all right, let's just dig a little bit more out of this and see if you understand what's happening mechanically. Okay, so then this one says, right, what kind? If Calvin's mass is 70 kilograms, yeah, be careful. The total, they have a total combined mass of 200 kilograms. But now we're just saying, hey, if Calvin has a mass of 70 kilograms, what is the magnitude of the force that the cage exerts on Calvin? So in this case, again, you could do a little free body diagram again, just to see what forces are acting on Calvin, right? And so that's what I did, is I said, yep, here's the bottom of the cage here, and then here's Calvin, right, standing right there. And it's like, well, what forces are acting on Calvin? Well, I got a mass times gravity doing this, right? That's always going to be there. And then I'm going to have it's in the way here. And then I'm going to have a normal force acting up on Calvin, right? And so then what the problem asked you, and that's it, right? That's the only thing that's acting on Calvin. And what the problem asked you is what's the normal force, right? What's pushing on the bottom of Calvin's feet, right? And what's pushing on the bottom of Calvin's feet is the normal force, right? And there's actually 2 ways you can get what that normal force is, right? And I think the easiest is to look in the, right? 'Cause you do the same thing. You apply those same equations. My equations of motion, some of the forces in the z direction. What's the acceleration in the z direction? 0. 0 is equal to negative mg plus the normal force times sine 45. Okay? And the only unknown in that equation right there is that normal force. So even just based off of Fz right there, you could solve for what the normal force is. Okay? And so according to this, the normal force is equal to 971.1 newtons. Okay? It's enough with that, right? Just because there's no acceleration in that direction, so then it just becomes a statics problem. But if you didn't see that, if you didn't look in that direction, you could also look in the ER direction, and we should get the exact same answer. Some of the forces in the R direction is equal to MAR, which is equal to, so write down what the forces in the R direction are. Forces in the R direction, we get negative N cosine 45 is equal to negative M times negative R omega squared. M times negative R omega squared, right? And if you put in the values there, you could solve for that normal force. Again, equals the same thing, which I'd be very alarmed if it didn't equal the same thing. Here. That's it, right? Again, that process just leads you down and takes you right to the answer. I messed around with a little thicker pen today. What's the little thicker pen stroke? Did you notice? You like it a little bit better? Maybe easier to see back in the back there? It was a little smeary though. They're kind of, but maybe better though. Any questions about this one? Yeah.
If in like a different problem, it was spinning faster.
Yeah.
So like you didn't have just the 1g of acceleration, but then you just have to look in the ER direction.
Nope, either one would work because that angle would be different, right? the angle would be more like this, right? And so for that normal force, the mass either one would work. As long as it's not accelerating in those directions, you should get the exact same answer every time. Yeah. It just so happens this time it's G. Yeah.
I found like the total acceleration first, by like the magnitude of gravity and then plus the centrifugal we had.
Yeah.
And then multiplied that by the 70. Does that work or?
I have no idea what you just said. yeah. Maybe show me afterwards. Yeah, so I can actually see it. I'm not very, yeah. Try again, one more time, we'll try.
I had just the acceleration total is equal to the 9.81 from gravity squared plus 9.81 from the centrifugal acceleration we had.
We'll look afterwards. It is because gravity. It's weird because gravity is an acceleration, right? It is an acceleration, right? But we don't really ever talk about it being an acceleration. We just talk about it. We're putting it on the force side of the equation, so it's applying a force. So really, in this particular case, unless you let go of it and let it drop, it's not accelerating that direction, and so it's not so saying that it has an acceleration of G down and it has acceleration to AR is incorrect. Maybe you end up with the same answer, but it's not the same because it's not actually accelerating down with gravity. Does that make sense? Yeah. And it's a really common thing because I think sometimes in physics classes they treat gravity different. And the way we're treating gravity is it's going to be one of our forces. It's going to be mass times gravity. So the weight, it's going to be a force acting on it. And you can there's other ways to think of it where gravity is accelerating and you adjust your accelerations for gravity and stuff. But we're not going to do it that way. Maybe did that?
Yeah, it gave it the same answer. I just wanted to see if that was like a good idea to follow.
I don't like that.
Okay.
Yeah. Okay. Yeah. I like more just, here's my free body diagram, right? I look at it, I sum, back to the methodology, I sum my forces. It's just, the key to this one was just like, hey, like, let's just take a second. We have them lumped together, we solve lumped together, and then you could always do this. Then you can kind of come in and break it up into smaller pieces, and free body diagrams and stuff still work. I mean, you say what is exactly touching this guy, and what is his accelerations and stuff, and that's it. That's all that's acting on him. That's all that it can be, and then this thing comes out of it. And that same thing with mechanics of materials. When you're studying mechanics of materials, you can cut that bitch wherever you want, and it always works out. There's always equilibrium in every section that when you get into beam analysis. You haven't gotten to beam analysis yet, but or even statics, you just start cutting it wherever you're at, and it always works out. They always have to have static equilibrium. They always have to have dynamic equilibrium, if you will, for these things. Okay? You guys ready?
I just had a quick question.
Yeah.
If you added another tension force, would that create one of those same equations, or would you do like what tension is the ratio of the tension?
Well, if I added another tension force on this guy.
A particle with like two strings.
Yeah, like the homework problem. Yeah. It gets really complicated. And that's why the example or the homework that you did was when the other one disappeared, right? If you sped it up too much, then one of them went slack. And if you slowed down too much, the other one was slack. Because if it's somewhere in the middle, I believe it's indeterminate. And there's other ways you have to solve it.
You can't do like where T1 would be some percentage of T2 or...
I think it gets too complicated because I think it depends on the stiffness of the cables in between them, and it gets weird, and that's why the homework problem just has one goes away and the other one goes away. Otherwise, it's indeterminate, and I think it makes it because you have too many unknowns. You have too many unknowns to try to solve. Yeah.
We have 7 minutes left, by the way.
Okay. Yeah. Yeah, I can hear people. It's some group is meeting afterwards. The race car people. Hey, stick around if you want to. Cool. You guys good?
Are we moving YouTube Friday to Monday?
Yeah, we'll come up with something. Yeah, there's some good stuff.
That dude was taking notes.
Oh, he was. He liked it. Yeah, that's good. He questioning his major, so this is way cooler. Engineering's pretty cool. I mean, this is cool shit, right? I mean, this is neat, right? All right.